The last talk from Professor Mauro Pereira from Khalifa University at Abu Dhabi. We will talk about the GHz-THz Nonlinearities in Semiconductor Superlattices. I give you the floor.
So first of all, I would like to thank Abdelatif for pointing out this forum and for inviting me to give a talk here. And since January 5th, I'm the chair of physics at Khalifa University, and I also have a role at the Academy of Sciences in Prague, where I'm still a scientist and keep a small team of theorists. And the research which I'm presenting here today has been funded by GIGA-TERA, which is the Czech Academy Research Foundation, and by the European Union under the Aqua 3S project. So basically, I will start giving you an idea of the main applications that we target, then a brief outline of the theory and simulations. Remember that I actually am a full-time theorist. Then I'll show control of gigahertz and terahertz nonlinearities of materials per design, and then giant control of these nonlinearities using voltages. So the main applications which I am interested are applications to nonlinear optics itself, fundamental studies, the protection of water facilities using advanced sensors, and I hope that by next year our funding will start to use these devices that we are developing also for breath analysis. So the project is called Rhythm, and it will be the result of a collaboration with two companies in Europe, MIR-Sense and Ionico. So just to give you an idea of what our current main application project is, Aqua 3S, it involves a number of institutes and companies, as well as end users, which are water utilities, and the devices, software, everything being developed will be tested, and this will help improve the quality and security of water throughout Europe. So the research which I present today is related to intersubband transport and optics. I'm not sure if you are used to the difference. Conventional lasers and devices are based in interband optics, in which you have transitions between the conduction and valence band. Devices like those that I'm discussing here today, such as quantum cascade lasers and superlattice multipliers, are based on intersubband transitions. There are only electrons, and these have the advantages that we can have small energy transitions. We are not limited by the band gap. And then we can go to mid-infrared and terahertz ranges with transitions. And in the case of superlattices, we can reach also the gigahertz using nonlinear currents, which is the main topic of this talk. So the main technique that I use is non-equilibrium Green's functions. I don't know how to get rid of this. Yep. All right. So I use non-equilibrium Green's functions, and basically for the superlattices which I have, the Hamiltonian has a kinetic energy, the superlattice potential, a mean field, which is the charged particles were left behind when the electrons move due to an applied field, and this allows us to make predictive calculations for the response of the system. Basically, here I need to get the nonlinear current response. So I take into account a few scattering mechanisms in the second Born approximation. And the code which I'm using right now has electron impurity, interface roughness scattering, and electron phonon scattering. Here you see sigma lesser, which is one of the self-energies resolved in both frequency, and momentum. And these play a major role in our calculations. So basically, the main difficulty is to find good approximations for the self-energies which have enough of the physics and that is still programmable so that our codes converge. So this kind of formalism has been used by myself and colleagues over the years to describe quantum cascade lasers. Here you see our first simulator, which very successfully described lasers made in Sheffield. We have developed a simulator which now needs redevelopment, which gave a very good agreement with lasers made at the MIT. We have a new version right now, which I have been using. Actually, it's the simulator which I'm using here right now. And within the next couple of years, I hope to have a bridge between this model here and this one here. But for now, what we are using is sufficient. I actually am operating in a range where the full non-equilibrium code does not work. So what I do is to use input from the non-equilibrium code to semi-analytical approximations that allow me to describe the optical response of the current when I apply an extra field to it, when I apply a gigahertz field to it. So basically, with non-equilibrium Green's functions, I calculate the current, extract some parameters from it, and put it into the solutions of the Boltzmann equation that allow me to have an arbitrary value of this parameter here, this alpha parameter, and I cannot use it in the current non-equilibrium, the present non-equilibrium code, because I have large fields and small energies, and the code doesn't converge in this case. And this expression here always works. So my colleagues in Nizhny Novgorod make experiments, and they have been testing our theory in detail. What happens is that the current measured by our colleagues is not perfectly antisymmetric as predicted by usual theories. And we can actually describe that using the fact that the interfaces between gallium arsenide and aluminum arsenide are different. And we can introduce this in our non-equilibrium codes, and this gives rise to non-symmetric current flow. We also have the option of directly adjusting the current voltage to experiments and plugging that in our solution of the Boltzmann equation, which is something we have done and have used in the last slides, which I'll show here today. So the first experiments that were made were so that our colleagues measured both odd and even harmonics. And even harmonics are not supposed to be present if the current is as expected by usual theories. Completely antisymmetric current doesn't give even harmonics. Our theory predicts it, and you can see here that the agreement experiments is quite good. So this was the first theory, as far as I know, that could predict quantitatively those even harmonics. And we went several steps further. We also use the theory to actually understand what is the actual value of the electric field inside the resonator. We have, inside the waveguides, we have a complicated structure in which the superlattices are housed in waveguides. And the theory actually allows us to know what is the field inside by finding the best value of alpha that characterizes the experiments. We have done a number of numerical simulations in which we play numerically with deviations from ideal interfaces. And this parameter delta here is this measures this anisotropy in the current as a consequence of bad interfaces. And we have predicted increase in even harmonics and decrease in odd harmonics. And we have now a project in which we will try to make samples to look at this effect experimentally as well. So we have also analyzed the limits of the current of the existing sources and how they can be used for multiplication. And our simulations are in much better agreement with actual experimental data than all the theories that preceded us. So we have also gone a step beyond my solution, because my solution for the asymmetric flow is an ansatz. I don't have an exact solution of the Boltzmann equation in this case, and Apostolus, my postdoc, used generalized Chambers path integral method to solve the problem exactly numerically, and we have much better results with the numerical solution, and we are able to look into large changes in the symmetry. And as expected, as the symmetry increases for even harmonics, the output of the harmonic increases, and for other harmonics, the deviation from an ideal interface, and thus the deviation from an antisymmetric curve, reduces the harmonic. So we are now hoping to have these predictions, which have been published in Nanophotonics, measured experimentally with carefully prepared samples, which will be sent to our colleagues in Russia, and also will be analyzed by the femtosecond group in Prague, trying to look for defects that you see here. However, I have also predicted a strong change in nonlinearities by applying voltages to the superlattices. And here, if I could apply high enough voltages in the superlattice without destroying the superlattice, I would actually see those petals here. However, the superlattices that we have at our disposal at the moment cannot handle very high voltages without being completely destroyed in the presence of a gigahertz field. So we have made experiments, and my colleagues made experiments to try to see if my theory was correct, but we were in a lower range of voltages. But even then, the results are quite interesting, and I'm going to show them to you. So here is the experimental setup. My colleagues are using superlattices for both emission as sources and detectors. They have two backward wave oscillators, one that excites the superlattice to generate harmonics, and another used in an heterodyne mixing scheme. The advantage of this is that it can operate fully at room temperatures. We don't need cryocooling, we don't need bolometers, and we can take lots of data at the same time. So, of course, I have also developed the theory of heterodyne detection with non-symmetric currents. This will be the result of a dedicated publication. For now here, I just show the result for this case, in which the output from the superlattice multiplier is not very large. So you see here on top experiments, and in the bottom you see the predictions of the theory, and you see that even quantitatively we have very good agreement. The deviations from idealized behavior are due to noise, because at low power, here is the incident power. At low power, it's difficult to make this experiment, and we get lots of noise. But you see here that applying a voltage, I have orders of magnitude control on the output. And this opens new doors to not only nonlinear optics. We want to analyze a number of other effects here, but also allows us to try to create new devices in which we're going to have a number of harmonics. And we're making an effort to have, in the very near future, integrated gigahertz sources without multipliers to span a range of gigahertz frequencies and low terahertz, where quantum cascade lasers do not operate, like in here. Okay. And to summarize, we have both an activity on very fundamental physics and the development of new non-equilibrium Green's functions and hybrid solutions for the Boltzmann equations, together with nonlinear optics and transport studies, coupled with the development of new devices and direct applications to security, medical, and environmental applications. We work with a company called MIRSense. From next year, we'll be working also with Ionicon, and we plan to go all the way to keep going all the way from fundamental physics to applications. So thank you. If you have some questions, I'm open to answer them.
Thank you very much, Professor Pereira. Some questions from speaker side?
I do have a question here, believe it or not. Slide 17, the difference between AB and, no, sorry, let me check. So which one are for, am I correct, or some are for odds harmonic and some are for even harmonics? And are AC for even harmonics and BD for?
Exactly. This is the fourth harmonic. No, this is the third harmonic, fourth harmonic, fifth harmonic, sixth harmonic. So what do you see? The higher the harmonic, more power is needed to get nonlinear results. You see that the maximum is moving to the right. And you see that by applying a voltage, the other harmonics lose power, go through a minimum, and then they come back again. This is because there is the solutions of this problem are related actually to maxima and minima of a very complicated mix of functions, which create an interference grid in this power voltage space. And this here, you see that you can get almost the same power with a higher voltage, and you can get even harmonics, basically the same power that you would get here and there. Sorry, this is the other harmonics. For the even harmonics, you see that you can get sufficiently high voltages, very high powers as well. What is the deal about this? Why am I so interested in that? Because if I can have a superlattice, maybe the gallium nitride, that can take a lot of voltage, I can have very high power with high harmonics. So I can put 130 gigahertz and get room temperature terahertz output power with this. So we are working now in trying to improve both the antisymmetric behavior and the resilience of the superlattices to be able to make this a competitor to quantum cascade lasers in the range where they will never operate. Because at low frequency, low terahertz, they will never operate without very strong cryocooling, and this operates at room temperature. So my dream for covering a range which we can't do with quantum cascade lasers for high terahertz frequencies in mid-infrared makes no sense whatsoever to waste my time with this, because the quantum cascade lasers are the best devices you can think of. But this gives me a chance to look at a region where there are a number of resonances, mostly for biological substances that we want to take, that we want to detect both in the air, in the water, and in the body as well. And this will extend the range, for example, of our current devices for breath analysis to the gigahertz range.
Thank you.
Thank you for thank you everybody. Thank you to all speakers for the nice talks, and thank you for also thank you all the attendees which participated to the meeting.
Good night, everybody.
So
Yes.
see you tomorrow at same time at 4 o'clock, and have a good night or good evening.
Thank you very much. Thank you.
Thank you. Bye.